to day 11 of the 12 days of LiDAR. My name is Alex Bilk, and today we're going to be talking about terrestrial LiDAR or tLiDAR. I'm using that term to encompass everything from traditional terrestrial LiDAR to mobile LiDAR to other forms that we're going to talk about as well. So it's meant to be all-encompassing. I'm just using it for the sake of ease of use. Now, my experience when I started with terrestrial LiDAR was on systems like this. So a Faro terrestrial LiDAR system, and I'm going to play a video here in a moment so you can see how those function. These come from either the engineering world or they come from actually forensics is what they are generally marketed towards. So taking a unit like this out into the field was an interesting experience. What happens is the laser, it comes out of the unit here and hits that mirror, and the mirror spins. So imagine that this tool is taking a slice of the forest the width of a laser beam, and then it's slowly going to rotate 360 degrees and capture everything except for what's directly beneath it. Um, this unit is a little bit slower. Newer ones are faster. There's trade-offs with this technology. Um, but I had a project that was funded by Forestry Futures in Ontario where a field crew took this out and did 50 permanent sample plots with it. So to the full growth and yield specification in Ontario, as well as using this unit, and it survived. So I have to speak to their longevity. They are quite robust units, and I wasn't sure that that was going to be the case. What are some benefits if we talk about this idea of terrestrial LiDAR, mobile LiDAR? Um, I don't have any examples of the mobile LiDAR unit. The most popular one that I'm aware of for forestry use is called a GeoSlam. Take a look and Google some of the information there. It has trade-offs with the fixed units, but for forestry applications, there's maybe some benefits on being able to capture really dense stands by being able to do um, more coverage of an area a lot faster. The trade-off being this, you can get the same measurement every time, so you can get down to doing things like mean annual increment with a lot of confidence because you're taking the exact same measurements at the exact same point every time. So what are the benefits? Well, number one, field crews are expensive. Data collection takes an enormous amount of time. To give you an idea, for a permanent sample plot in Ontario, which contains 3 permanent growth plots within it, that was taking 5 days for 2 people to measure one plot. A lot of metrics involved in that. So what we looked at was seeing, could we remove some of that cost expenditure by replacing elements of it with terrestrial LiDAR. The other one is that we've got a permanent record. So I like to showcase this because it was pretty fun to get John Parton to put on the VR goggles and be able to interact with the data after the fact. We could break it up, we could have it go through and do all kinds of different elements in this data set to understand what the heights were, what the different breakpoints were, and interact with it. We were utilizing a piece of software that was designed to work with virtual reality, so that you could actually move through the stand, conduct virtual measurements, interact with the data. This was all very early on in this technology, but it was pretty interesting to be able to see it that way. Being able to go from the point cloud here, isolating trees, and then going for things like diameter breast height measurement and understanding that there are trade-offs in how we do circle fitting, how we do estimating that, what the error is associated. There's a lot of different approaches to try to do this analysis. We are not going to go into the software, the calculations, the assessments of this. I just want you to see examples of this type of data collection and what's involved in it. What are some challenges with terrestrial LiDAR, though, or any kind of LiDAR like this? Well, one, it's expensive. Those units are not cheap. The unit being used there costs more than the pickup truck to drive the crew there. So it was very expensive. They can be delicate. I mean, they survived because the crew worked smart with it. But you're hiking through tough terrain, dense brush. There's a trade-off there. Mobile LiDAR units, same thing. They're fairly robust and they're a lot smaller to pack in. But you still are worried about if a crew trips and falls on it. It's a delicate instrument. Bad weather is another challenge. So the unit was IP43 rated and could handle a light rain, but data quality becomes a significant problem. And even if you've got no rain, but you've got a lot of moisture in the air, we were noticing significant errors associated with it. So this was a challenge. Especially where this came in was condensation on the mirror. It's easy to overcome, but it's easy to miss. So if you took the unit out of a warm truck into a cool environment, and just like with a camera lens, it would fog up. And if you didn't catch that error, you were in for a world of trouble because you spent an entire day collecting and you didn't actually have workable data sets. Um, the nice thing with the terrestrial LiDAR unit is that we do get colorization as an option as well. So being able to interact with the data and actually take photos and attach those together can be quite nice when it works. The problem with that approach, though, and you have to be aware of this, is that the images can sometimes hide problems. So in this case, the photo looked fine, but the point cloud was a problem. What was going on here was wind. There are a lot of algorithmic approaches to try to deal with this. If we're trying to do height assessment, all those sorts of things, um, there are trade offs with this technology, and you're going to get noise. The speed of the sensor, the type of data you're collecting, and also, do you need to use it for height? I mean, that's honestly a question that you start to ask here. Is if you've got wall-to-wall LiDAR, is this to fill in the diameter breast height gap to help build better models? Maybe we don't care about this error. Maybe we don't even try to collect it. But those are the trade-offs you have to be aware of with this technology. I want to show you a fantastic video. It comes from Temple University, and they built all of this in Blender. But conceptually, what it shows is the power of this type of data. So we're just going to watch this together. It's called 3D forest information. The idea is, again, in terrestrial LiDAR, you collect from several locations around a plot and you co-register it into one large point cloud. This particular one has 20 million. A lot of the ones that I was collecting with that sensor, especially with dense underbrush, we were into hundreds of millions of points. Very dense data. What you want to do then is tie it into the ground, identify the bottoms of the trees if you can. Underbrush again becomes a challenge here. It's not perfect. This is sort of an idealized version of it, but it is possible. You can separate those points, those trees fairly reasonably. Crown separation becomes a problem depending on stand development. But then what we want to do is take that point cloud and turn it into cylinders if we can. Again, it assumes that we've got good look angles at everything. We've got adequate coverage to be able to do that. But we fill in those gaps and we can do cylinder fitting or voxels, another approach to this. There's a lot of different approaches. This is just one idea where we can then quantify volume, taper models, and everything else. One project that we did as an extension in Ontario was to start collecting stem taper um, where they were doing destructive sampling so that we had an absolute measure of volume from destructive sampling and the terrestrial LiDAR scans of the same exact tree being able to come up with models there to understand the implication, because if we could expand the number of samples to drive taper equation development, it's very beneficial, especially with understanding different stand conditions. So that's a really interesting way of looking at this. I really appreciate this graphic, so that's why I like to show it. But they used real point cloud data to build all of that. I'll just let there you go, so that the proper credit is given. All right. Now, there is another sensor out there that's available. I sort of alluded to it, and that is that in the iPhone 12 Pro series, as well as the iPad Pro, there's actually a built-in LiDAR scanner. The purpose of it is to help with focus control, but we can actually access that sensor and utilize it to capture data. The data sets that I'm going to show you come from a project that was done by these folks here. This was at Silva Laser, I believe, in 2021. So check out this paper if you're interested in more of the background data of where this comes from. But we're in Poetry Viewer right now, and we're looking at a terrestrial LiDAR scan, and you see that we get a lot of the tree bowl here. We can actually zoom in, so we're getting a lot of height information. This is where terrestrial LiDAR really comes in. It can capture a long distance. Mobile LiDAR, I believe, limits out around 15 meters. That may have changed with newer technology, but generally speaking, you're getting partway up the tree, but you're probably not reaching the tops. So that's one major difference between mobile and terrestrial. And then what they utilized was 3 different apps on the phone to try to see what can we get for point clouds. Now, the range on the LiDAR on the phone is not that big, so we're going to zoom down here. Before we get into it, though, I want you to see these shapes right here. Make a note of those. Those are co-registration spheres. And when we talk about trying to utilize terrestrial LiDAR or any technologies like that, they rely on having these targets so that they can calibrate where they are, compute the geometry here with known objects of a known size, and known reflectance, so that they can figure out any error associated. And these spheres are quite expensive, actually. We paid several $1,000s for a set of 6 of them, so that we could have exact size, known albedo, known reflectance, but what they do is give you that calibration and error assessment. If you were deploying this at scale in the field, you likely wouldn't utilize those. You might use some paper targets, but that's the trade-off again here. So we see all of the data here. What I'm going to do is turn this off and turn on my first set of iPad Pro collected data. And you see now that we get fairly reasonable dBH reconstruction here. Not perfect in some cases. There's going to be noise here. We could clean up some of this. But I just wanted to show you a few different captures where they trade off noise for smoothing and compare it to the really expensive sensor, because a field crew carrying, an iPad Pro or an iPhone 12 Pro or newer Pro model with the LiDAR built in can start to collect information like this. Now this one is black. Let me just find. There we go. So we've got DBH and then, or sorry, we've got DTM pulled out here. We've got we've got ground keyed out in all of these. So it's gone through an initial classification, and then we could compare and contrast these. And we see that from a tree identification perspective, most of the tree boles have been identified fairly reasonably. There's a bit of a shift here, depending on which point cloud we're looking at, especially say this one right here. If I take my background one, let me just make this a set color so it pops out. You can start to see the shift that occurred there. Maybe the geometry is not quite perfect. That's an example of some of the mobile LiDAR algorithms, but this is also 2 years old. So collecting this with newer apps, newer versions of it, may yield different results. There's also not a lot of understory here, so it is pretty good conditions for terrestrial LiDAR. But what I want you to take away from this is the art of the possible. It's the potential to be able to tap into these types of technologies and keep pushing this boundary so that we can look at it. There's fantastic work going on in Europe. There's a cost action around it. Dr. Martin Makoros, I urge you to check out some of his work to understand it, where they're looking at things like mean annual increment, and the potential of this is going to be exciting. When we talk about LiDAR and data fusion, this idea of plot level data, being able to see the trees from the side using terrestrial or mobile LiDAR, and then high density aerial LiDAR, fusing those data sets together to get the best of both worlds, is a pretty exciting space to be in when we talk about forestry, carbon accounting, or any of these spaces. So with that, thank you very much for listening, and tune in tomorrow for a final wrap up where we discuss everything you've learned in the last 11 days and where it might be worth your time to invest going forward if you want to continue to grow your knowledge in this space. Thank you very much for listening.